In this chapter, we study Lagrangian mechanics. The Lagrangian mechanics is equivalent to the Newtonian mechanics, except that it begins with action. And action is the time integral of the Lagrangian, and Lagrangian is the kinetic energy subtracted by the potential energy. The difference between the Newtonian mechanics and the Lagrangian mechanics is that the equation of motion is the beginning point of the Newtonian mechanics, F equals ma. Double time derivative of position is related to the force applied to the system. The Euler-Lagrange equation is equivalent, although it is equivalent to the equation of motion of Newtonian mechanics. The different thing is that force can be computed from the scalar function, that is potential energy, and momentum is obtained from the kinetic energy. So as you know, if we apply some force, the momentum changes depending on the amount of work. Time rate, for example. Okay, so Lagrangian mechanics deals with action. Action is the time integral of Lagrangian, and Lagrangian is a kinetic energy minus potential energy, that is a scalar function. And the integral of that scalar function, integral of the Lagrangian, is action. Anyway, we end up with the same equation. This is the equation of motion, but this equation of motion, left hand side and right hand side are in a different form. But in the case of Euler-Lagrange equation, it begins with the same function, a single function that is called Lagrangian. So Lagrangian's some projection onto the velocity space and some projection onto the coordinate space gives a different contribution. For example, the partial derivative of the Lagrangian is related to the partial derivative of the potential, and that is actually the force. All right. Let's begin with the definition of kinetic energy. We already know very well. Definition of kinetic energy is 1/2 mass times velocity squared. And velocity squared in three-dimensional space is a sum of x velocity and y velocity and z velocity squared. If I make use of the Einstein convention, the kinetic energy is expressed in terms of 1/2 m xi dot squared, where I is summed from 1 to 3. As we know, the momentum, linear momentum, is mass times velocity. The velocity is momentum divided by mass. Therefore, if we substitute this one into the kinetic energy formula, the kinetic energy can be expressed in terms of momentum. That is a p squared over 2m. Although these two expressions are the same, we use p squared over 2m to represent the kinetic energy in the case of Hamiltonian mechanics. Hamiltonian is in a simple case, Hamiltonian is just the total mechanical energy of the system. While Hamiltonian system has the kinetic energy expression of p squared 2m, in the Lagrangian mechanics, kinetic energy must be written in terms of x dot, that is velocity. So 1/2 mv squared is this, not v, but x dot. Expression should be written in x dot instead of v. The kinetic energy must be written in this form in the Lagrangian mechanics. Let us look into some partial derivatives of the Lagrangian. Lagrangian is the difference of kinetic energy and potential energy. Kinetic energy is 1/2 m xk dot square and u minus u. And if we take the partial derivative with respect to xi dot, that is the velocity, we know that we are considering the velocity independent conservative force. That means potential is a function of x only. It does not have any explicit time dependence. So, for example, potential's partial time derivative is 0, and the potential's xi dot dependence, this partial derivatives are all 0. That is a velocity independent potential. So if I take the partial derivative of L with respect to xi dot velocity, then the contribution of the potential energy vanishes, and the only surviving term is the contribution of kinetic energy. Chain rule can be used to carry out this partial differentiation, and this one is 2 times xk dot, and xk dot should be taken the derivative with respect to xi dot. So we have xk dot derivative with respect to xi dot, and because they are the same except for the vector indices, it should be Kronecker delta. So Kronecker delta k. So we have 1/2 2 cancels to have m and xk dot and delta ik. And xk dot is a momentum, linear momentum, k component of the linear momentum multiplied by the Kronecker delta, which gives pi. So what we find is in the Cartesian coordinate system, partial derivative of the Lagrangian with respect to the velocity is momentum, which we call the conjugate momentum. And then if I take the derivative of the Lagrangian with respect to the coordinate, as you know, the kinetic energy depends on the velocity, xk dot. Therefore, if I take the partial derivative with respect to the coordinate, this contribution vanishes and only the potential energy contribution survives. We have a minus minus a plus. So this is gradient u if I multiply the unit vector for the ith component and sum over I. So you know minus gradient of potential energy is the force. Therefore we have a minus force of that ith component of the force. Therefore this is called the Euler-Lagrange equation. So let me write down the Euler-Lagrange equation and substitute this region. This is velocity derivative of the Lagrangian was the conjugate momentum pi. So we can write this one, replace this one with conjugate momentum pi. And we have the time derivative. So this one becomes time derivative of the ith component of the linear momentum. The next one is a partial derivative of L with respect to x multiplied by minus 1. That was the ith component of the force. So minus Fi is, this one is replaced with minus Fi. If I move this F contribution to the right side, what I find is time derivative of ith component of linear momentum is the ith component of the force. That is, if I collect the three components all together, then we have a vector equation. This vector equation is F equals momentum's time derivative, F equals ma. This is Newton's second law of motion. In summary, the Euler-Lagrange equations are nothing but a component-wise expression for the Newton's second law. So here, momentum can be obtained by taking the partial derivative of Lagrangian with respect to the velocity. Then we have a conjugate momentum, and bring out the conjugate momentum and take the partial derivative, take the time derivative, that is momentum's time derivative, pi dot. And this one was found to be the force. So force can be obtained by taking, the force is minus the gradient u, and P is I hat this kinetic energy, and this one is in the this right side. This one can also be obtained from the Lagrangian, and this one can also be obtained from the Lagrangian. So momentum and force can be derived directly from the Lagrangian. So momentum can be derived from the partial derivative of with respect to the velocity of the kinetic energy. Force can be obtained from the by taking the minus gradient of the potential. So this is exactly the same equation, except that this momentum and force are derived directly from the Lagrangian. So this equation looks complicated in comparison with this, but in the sense that we just memorize this formula, but in this case it does derive from a single function that is called the Lagrangian. That is the main difference between the Newtonian mechanics and the Lagrangian. And this is not the end of the day. And we will find that this equation holds if I require some restriction that the action, that is the time integral of the Lagrangian, should have some minimum value. In general, it has an extremum value, but in fact, it is a minimum value, along which the physical path is realized. Okay. We summarize what we have done until now. Kinetic energy is the 1/2 mass times velocity squared. And kinetic energy, if I take the partial derivative with respect to the velocity, that is xi dot, then I can collect, it ends up with the mass times velocity, that is the linear momentum. And the Lagrangian, if I do the same job for the Lagrangian, because we are considering the time-independent potential energy does not depend on t explicitly, does not depend on x dot explicitly. So this contribution vanishes, and only the kinetic energy term contributes, and that is the linear momentum. So Lagrangian's partial derivative with respect to the velocity is called conjugate momentum. Conjugate momentum is very important because x has a conjugate momentum p, angular theta has a conjugate of the angular momentum. And actually, these conjugate momentum has a very important relation in the quantum mechanics. In classical mechanics, we shall find that the Poisson bracket analysis is extend to the commutator of coordinate and its conjugate momentum, and fundamental commutation relation for the quantum mechanics is the commutator of x and p, right? And commutator of x and p says it's x and p's commutator should be the same as angle and angular momentum's commutator, because angle gives the conjugate momentum that is orbital angular momentum, right? And again, momentum, in summary, momentum is pulled out from the Lagrangian by taking the partial derivative with respect to the velocity, and force can be obtained by taking the minus gradient of the potential energy. And the Lagrangian, which is t minus u, has the contribution to find the momentum by taking the partial derivative with respect to the velocity. It has some force information about force, so we can take the derivative with respect to space and put the negative sign on the potential energy, then we can obtain the force. And in this derivative, this kinetic energy contribution vanishes. So the force can be obtained by taking the gradient of a Lagrangian in the Cartesian coordinate system especially. And this is the basic relation that derives the equation of motion. That is the Euler-Lagrange equation of motion. Next, we study how we derive the Euler-Lagrange equation of motion. Until now, we just have shown the equivalence between the Euler-Lagrange equation and Newtonian equation of motion. Once we introduce the Lagrangian, the Euler-Lagrange equation is related to some minimization of action. We will find that if we define the action in terms of the time integral from a certain beginning time to a final time, that integral is defined to be an action, and the physical path. Physical path means the path along which the equation of motion is satisfied. And along the physical path, the equation of motion is satisfied. However, we can imagine some unphysical contribution, an unphysical path. For example, this is a path, this is time, and this is the trajectory. Y-axis, the position of the particle at time t. And blue straight line shows this is a straight motion. If there is no force, it goes straight, and slope is the velocity. So let us assume that this particle starts at the origin and arrives at this point at time t2. And this is a free motion of a particle, and we say that this straight line is the free trajectory of that free particle, and that actual trajectory of the particle is called x physical. Now we vary this physical path from the original physical path to unphysical path. The variation will be made under the restriction that the starting point and end point does not change at all. However, let's assume it is moving different from the original physical path. The amount of shift, this is called the unphysical subtracted by physical, is called to be the delta x. This delta x is the variation from the physical path to the unphysical path. We shall find this is the action. Action as is defined to be the time integral of the Lagrangian, and we apply the least action principle to minimize this integral, and the condition of minimization of this integral is the same as the Euler-Lagrange equation. And on the previous page, we have verified that as long as the potential is independent of time, it does not have explicit time dependence, and the potential has no explicit velocity dependence, then the equation of motion, Newton's equation of motion, was exactly the same as the Euler-Lagrange equation. And actually, the Euler-Lagrange equation is the condition for having this action to have a minimum value or extremum value. Again, this is a blue path is the trajectory of a particle, and this is the beginning time and the end time. Start, end. And the variation from the physical path to unphysical path is made with the restriction that the variation at the two endpoints, delta x t1 equals 0 and the delta x t2 equals 0. If we do not allow this, it is just a nothing. It is not absolutely unphysical. It is just imagination. But what we want to do is actually we want to study the region near the physical solution. If it is even out of range, then we cannot approach the physical answer in any limit. So at least at the end of the day, you will find that this unphysical variation should vanish in the actual physical path. So in order to do that, we cannot shift we cannot allow the variation at the end points. At least it will merge to the physical path when the action is minimized. If it is not the case, it does not approach the physical path. So we cannot compare with the original value that is evaluated on the physical path. This is an example of shape of the variation. This variation doesn't have to follow any special form. It is either this is physical and unphysical. Unphysical may have any kind of form, except that it should have a single value. It should have a single value, and the endpoints are fixed to meet the physical path. Again, we state that the variation at the endpoints must not be allowed. The variation will be made on the Lagrangian, and actually eventually variation will be made on the action, and we find that this is a physical path and this is unphysical path, and the difference is the variation. And we remember that the variation at the endpoints at T1 and T2 are all vanishing. If I take the time derivative of both sides, what we find is unphysical velocity and physical velocity and velocity of the variation. So this is the correct expression, but we can also write in this kind of form. So variation of velocity is always computable. We can always compute the variation of the velocity by taking the time derivative of variation, right? Actually, if we vary the action, we first vary the Lagrangian, and Lagrangian is the integrand of a time integral. And Lagrangian has a kinetic energy and potential energy. Kinetic energy depends on the velocity, and potential energy depends on the position, x, the coordinate. So we can apply the method of Taylor series expansion for the multivariable function. We recall that the shift of a function by amount of a can be made by multiplying the exponentiated operator to f of x. And if we replace this a with the delta x and substitute that formula, we obtain this expression. And the shift of the function due to the shift of the variation from the physical path to unphysical path, that can be defined to be the difference of that function. That variation of the function can be made with this formula. The leading contribution is delta x dot gradient f, and second contribution is 1 over 2 factorial delta x dot gradient f squared, and so on. In the limit delta goes to 0, we do not have to consider the square contribution at leading contribution. So linear contribution will be considered now. All right, so let us substitute Lagrangian to f. And we have two variables, x and x dot. And Lagrangian is function of kinetic energy. Kinetic energy function of x dot, and potential energy function of x. So for the time being, we replace x dot by y. Then we can make use of this relation, f of y plus delta y, x plus delta y subtracted by f of y x. So I have a linear contribution. Y is partial derivative multiplied by y shift, x partial derivative multiplied by x shift. Now we return to the fact that f is Lagrangian and y is x dot. We substitute that Lagrangian's partial derivative with respect to the velocity multiplied by the variation of the velocity. And actually we know that the variation of the velocity is velocity of the variation, and x partial derivative multiplied delta x plus higher order pieces. So the variation of velocity is the time derivative of the time derivative of variation. So we substitute this. So variation of Lagrangian is summarized in this way. But we remember f a b prime. This comes from DAB equals DAB plus ADB, right? So this AB dot equals AB's dot subtracted by BA dot. So using this method, they usually used for integration by parts, we obtain this. So derivative of both of them, this is conjugate momentum of x, right? Lagrangian is taken, we have the partial derivative with respect to the velocity, so it is a conjugate momentum P corresponding to the coordinate x. And now we move this derivative to this conjugate momentum minus conjugate momentum's time derivative. Now delta x, the variation, is pulled out from the derivative, and then we have variation of Lagrangian with respect to the x. These two terms are proportional to the variation delta x. So we combine these two and leave the total derivative term in here. And this one, Lagrangian's partial derivative with respect to x subtracted by time derivative of conjugate momentum. Now we find that this one is actually if I put this one equals 0, what happens? This one is just equation of motion. This is Euler-Lagrange equation. Euler-Lagrange equation. Okay, this is the variation of the Lagrangian in the one-dimensional case, and we can simply extend this method to the three-dimensional case. You know, the Lagrangian in 3 dimensions is a function of x1, x2, x3, and x1 dot, x2 dot, and x3 dot. Therefore, the variation through the velocity should be made for x1 dot, x2 dot, and x3 dot, and we have to sum over I equals 1, 2, 3. In a similar manner, we can expand the variation contribution through the variation of x. So x1, x2, x3 contribution should be obtained by taking the partial derivative with respect to xi and multiplied by delta xi and summed over. As we have done in here, the variation of velocity should be written in the form the velocity of the variation. And then this method is also used to find the total derivative of this momentum multiplied by variation. This conjugate momentum Pi multiplied by the variation delta xi subtracted by the variation delta xi and the negative sign, this negative sign, derivative of the Pi, that is conjugate momentum of xi. And this one is copied in here. Again, we have the contribution that is a total derivative and plus something multiplied by delta xi summed over I. That means this one is the left-hand side of Euler-Lagrange equation for 3 dimensions. Right? Now, let us continue to find the relationship between the action and this variation. We have completed the variation of the Lagrangian in this form, where I is summed over, and this guy is the left-hand side of the Euler-Lagrange equation. And actually, what we have found is delta L. Let us substitute in here. Variation of action. Action is the time integral of the Lagrangian from time t1 to t2. And variation of this one is actually the time integral of the variation of this Lagrangian. And to the first order, leading order correction by the variation of delta x I, we can substitute this expression, neglecting order delta x squared or higher. If we substitute this into the integrand delta L, then what we find is the total time derivative of product of conjugate momentum multiplied by the coordinate variation, and next piece is integral of the left-hand side of Euler-Lagrange equation multiplied by the variation and summed over I. The first term is total derivative. Therefore, this value, rounded over xi, delta xi, evaluated at t equals t2, subtracted by, that is missing, conjugate momentum, multiply the variation at the end point t1. We find that the variation at the end points must vanish. That was our requirement. So this one vanishes, and the only integral is this one. All right. Our Euler-Lagrange equation is everything is zero. If action has some maximum value or minimum value, its derivative should vanish. And this is a double derivative here, as the prime should be 0, as a double derivative should be decreasing. And this is again this double derivative to be increasing. So if we require delta x equals to 0 for any delta xi, any variation, for any variation delta s equals 0, that means in this case the s is an extremum. So this is arbitrary multiplication, integrated. So something delta x1 plus something delta x2 something delta x3 dt. This integral t1 t2. This integral is 0 for any delta x, any delta x2, any delta x3. That means something 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 must be 0. Okay, so Euler, we have to obtain the Euler-Lagrange equation. So condition of the Euler-Lagrange equation is that the action has an extremum. The action has an extremum. Then Euler-Lagrange equation derives automatically. So in summary, F equals force equals F equals ma. This is Newton's laws of motion. This Newton's second law of motion. We have shown that this F equals ma is equivalent to the Euler-Lagrange equation, and actually if we require action to be minimized, then the Euler-Lagrange equation is automatically satisfied. So writing F equals ma, this one and this one, all three are equivalent. So what is simple? This one is simple. Although the derivation looks complicated, this one is simple. And this one, both of them are scalar. And this is a vector. But although they are scalar, we obtain by taking the derivatives of the vector equation. There are three equations. And Euler-Lagrange, the Lagrangian method is equivalent, absolutely equivalent to the Newtonian mechanics. Next, we consider the least action principle. Least action principle is already we have studied. Next, we consider this is the first form of Euler-Lagrange equation, but we can also think about the second form. And second form of Euler-Lagrange equation is very important because it directly relates to the Hamiltonian. Okay, this is phase space. Phase space means x and x dot space. The trajectory of x and x dot on a phase space describes the motion of particle absolutely. Because the equation of motion is a second-order linear differential equation, the trajectory is completely determined by a function and its own derivative. And second-order derivative are automatically defined by it's a differential equation. So MA means A is mx double dot. Mx double dot equals force. Force divided by mass is determined. So because of that differential equation, this phase space completely determines the mechanical system. Okay, in this plane, for example, if we consider the total mechanical energy of simple harmonic oscillator, the kinetic energy and potential energy sum is the energy that is a constant of time. And on this plane, x dot plane, it is an ellipse. So here it says the physical path of a mechanical system in the phase space is the path on which the action S has an extremum, that is the least action principle. Okay, this is the first form of Euler-Lagrange equation. Let us multiply velocity, both sides. Then what we obtain is, this is a force. This is a force. t minus u. So this is a minus. If I do not include this minus sign in here, it is just force. Force times velocity. That means force times velocity. That is power. What we want to do is we compute power. Power. Okay, if we integrate over time of the power, then it means we are computing some work. If we compute some work is related to the potential energy. Work is related also to the kinetic energy. If we do some work to a system, the kinetic energy will increase. If the potential energy does work on a system, the potential energy will decrease, something like that. Anyway, if we multiply the velocity of both sides, and again, we'd like to put this derivative to the left-hand side. All right. Then, if I take the derivative, this term is the derivative of this momentum. However, I have added the double time derivative of xi. So I need to subtract that contribution, double time derivative of x. And this one is copied. We recall that, in general, Lagrangian is a function of xi and xi dot. But let us allow the time dependence too. Most general form of the total time derivative of Lagrangian should be the sum of the partial time derivative of the Lagrangian plus xi dot. This is force, right? And then time derivative. So partial derivative of x and time derivative of x. Partial derivative of x dot and time derivative of x dot, so xi double dot. If I put negative sign on both sides, when we have this, and minus double dot, single dot should be, if I move this one to the left side, then partial derivative of L, partial time derivative of L, subtracted by total time derivative of L. Alright, so if I replace this one with this one, okay, here, this total time derivative of Lagrangian can be included in here. So, velocity, conjugate momentum, subtracted by the Lagrangian, and the partial time derivative term appears here. This one is to move to the right-hand side. We find this is actually the Hamiltonian. This is actually Hamiltonian, and then equals a minus partial time derivative of Lagrangian. This is called the second form of the Euler-Lagrange equation. In this equation, we find that as long as there is no explicit time dependence on the Lagrangian, then partial time derivative of Lagrangian vanishes. That means this one equals 0. If it is 0, then this amount, this is Hamiltonian. Actually, the Hamiltonian must be written in terms of x and p instead of x dot. We will find in the next chapter. And this Hamiltonian is independent of time. So this will become a constant of motion. So when the Lagrangian has no explicit time independence, the Hamiltonian is actually the total mechanical energy of the system, and the total mechanical energy of the system must be conserved in such a case. let's take a break. Okay, in the remaining 25 minutes, we review what we have learned today. The equation of motion, Newton's second law, equation of motion, force is the time derivative of momentum, is equivalent to the Euler-Lagrange equation. And Euler-Lagrange equation is this one. And here, the time derivative of momentum. This is momentum. Momentum is xi dot derivative, partial derivative of Lagrangian. And this one is a force. Force is minus a gradient of potential energy. This is possible if we define the Lagrangian to be the kinetic energy subtracted by the potential energy. It is because the kinetic energy has dependence of velocity, and potential energy, in this case we do not consider the velocity dependent potential or time dependent potential. If the velocity is the potential energy is independent of velocity, then Lagrangian's partial velocity derivative is the conjugate momentum pi. If it is the conjugate momentum pi, this one will be the time derivative of conjugate momentum. And because the kinetic energy is independent of coordinate, it is just a time derivative of coordinate velocity. Thus, the Lagrangian's partial derivative with respect to the coordinate is the force. Therefore, the Euler-Lagrange equation and Newton's second law are eventually the same thing. Later, we will find the kinetic energy expressed in terms of p squared over 2m in the Hamiltonian mechanism. But as far as Lagrangian mechanism is concerned, we always have to write the kinetic energy in terms of x dot. The velocity partial derivative of the Lagrangian is the momentum, and we call this momentum to be conjugate momentum. Conjugate momentum. And the coordinate and conjugate momentum has a special relationship, especially in quantum mechanics. The fundamental commutation relation, IH bar, the commutator of x and momentum is IH bar, that is coming from this relation. So coordinate x has the conjugate momentum, that is linear momentum, coordinate angle, whose conjugate momentum is angular momentum. The angle and angular momentum and coordinate and linear momentum, they have a relationship, a conjugate relationship. All right. In order to derive the equation of motion, although the equation of motion in Newton's Newtonian mechanics does not derive, it is stated directly. However, if we introduce the Lagrangian, then F equals ma, F and P are some derivatives of Lagrangian. Lagrangian is a spatial derivative. It is related to minus gradient u. That is the force. Lagrangian's velocity derivative is the momentum. So the equation of motion, Euler-Lagrange equation of motion, is equivalent to the Newton's second law and it derives from the single scalar function t minus u, that is the Lagrangian. And what we want to do next is the equation of motion must be some requirement for some condition. Then we shall find that this relation can be obtained if we minimize the action. And the action is defined by the time integral of the Lagrangian. And if we fixed the beginning time and its position and the final time and position for the path of a particle, which matches the physical path at the endpoints, and allow the variation from the physical path to unphysical path. And even though we allow such kind of variation from the physical path, we shall find that the action has the minimum value only when it approaches the physical value. So, although this is what we want, absolutely, this artificial modification of the path from the physical to unphysical, we conclude that the action is minimized. Once action is minimized along this path, then this one is the same as the Euler-Lagrange equation. Variation of the path from the physical path to the unphysical path should be continuous, and it should be differentiable to carry out the analysis. And additional restriction is that both endpoints has the fixed value for the variation. So delta x at the endpoint must vanish. So that if we approach, if we let delta x goes to 0, this unphysical path should approach the physical path. So that is the reason why the endpoint was restricted to be the same as the physical path. If it is not the case, unphysical path can never approach a physical path. So it is not a correct description of the problem. As long as endpoints of unphysical path is fixed to the physical path values, we do not care what kind of shape the unphysical path has. So variation can be made in a various way, except that the endpoints are fixed. While the variation of path can be obtained by subtraction of unphysical path subtracted by the physical path, the variation of the velocity is actually the time derivative of variation. So delta x dot is actually defined by the time derivative of the variation from the physical path to unphysical path. And in order to find out the change in the action, we first consider the variation of the Lagrangian, that is, integrand of the action. So, because the Lagrangian is a function of x and x dot, we have to consider the multivariable function variation. There are two variables, x and x dot. Lagrangian's variation due to the variation of the physical path to unphysical path, we were able to expand this by taking chain rule. The Lagrangian partial derivative with respect to the velocity and the variation of the velocity. Lagrangian's partial derivative with respect to the coordinate multiplied by the variation of the coordinate. And the variation of the velocity was defined by the time derivative of variation. The variation of the velocity was time derivative of variation. Because of this, we could write this one as time derivative of the variation, and this conjugate momentum can be included in the total derivative, and we have the total derivative, and the variation is pulled out from the derivative. Instead, the conjugate momentum derivative survives. So if you combine these two pieces, what we have that is proportional to the variation of the path is just left-hand side of the Euler-Lagrange equation. And the first piece is the total time derivative. So if we extend this one to the three-dimensional case, we put the subscripts in the vector indices from I runs from 1 to 3, and we have to sum over all the indices. This variation of Lagrangian should be substituted to the action formula to find out the variation of the action. The variation of the Lagrangian is substituted to the variation of the action. So variation of the Lagrangian is substituted in here. And the first piece, the total time derivative contribution, is integrated out. And we have variation at the endpoints T2, variation at the endpoint T1, whose coefficients are the conjugate momentum at the endpoints. And then we have sum of integrals depending on the independent variations. All the coordinates can be made, or the variation of every coordinate can be made independently. So this arbitrary contribution gives 0 when this delta S is 0. So minimizing the action, the least action principle requires that coefficient of this arbitrary variation must vanish everywhere for any indices independently. So we derive the Euler-Lagrange equation from the requirement that the action should be minimized. In this analysis, we do not distinguish from the maximum or minimum, but it is actually the minimum value. We say that the total derivative contribution has the variation at the endpoints that vanish absolutely, and coefficient is conjugate momentum. Next, we consider the second form of Euler-Lagrange equation. Euler-Lagrange equation was in this form, and we multiply the velocities. If we multiply the velocity, then this is a force. L equals to T minus V. Kinetic energy disappears. Potential energy minus gradient. This is Fi. So Fi xi dot. This is F dot V, right? So this is power. So this is something related with power. So if we integrate over time, this power becomes a work. So this is related to work, time rate of work. So if I multiply the velocity in here, insert this velocity inside the derivative, and we end up with the remnant term. That is a double time derivative of x. So that should be subtracted to have this one to be equal to this original term. And if we move this one, if we write down the total time derivative of the Lagrangian, it should be in general a sum of partial time derivative, and because Lagrangian is a function of x and xi dot, and we take the derivative and then use the chain rule, multiply xi's derivative, time derivative, xi prime, xi dot's time derivative. Okay, multiply negative sign, you find that this one is actually, if we move this one to the left hand side, partial time derivative of Lagrangian subtracted by the total time derivative of Lagrangian. And in here, total time minus total time derivative of Lagrangian can be included inside the total time derivative. And remaining piece is this one. And this one to be moved to the right hand side to find out the Hamiltonian. Hamiltonian should be written in terms of momentum and x. Anyway, this one is this. And this one is called the second form of Euler-Lagrange equation. And in case Lagrangian is independent of time, Lagrangian does not have any explicit time dependence, then this one disappears. That means the Hamiltonian is constant of motion. Alright, so we just have found that the second form of Euler-Lagrange equation. And Noether's theorem states that if Lagrangian is independent of coordinate, then we say it is a cyclic coordinate. If xi is a cyclic coordinate, then the corresponding conjugate momentum is conserved. Let's see. This is Euler-Lagrange equation. If this partial derivative of Lagrangian with respect to a coordinate is 0, then we say it is xi is a cyclic coordinate. If it is cyclic coordinate, then this one is equal to 0. Then if it is 0, then time derivative of this is 0. Actually, this is the conjugate momentum. If Lagrangian is independent of coordinate, then that coordinate is called the cyclic coordinate, and the corresponding conjugate momentum is constant motion. For example, if we do not have any potential energy, any finite potential energy that does not depend on position, constant one, we just put u equals to 0. In that case, Lagrangian is t minus u, and the kinetic energy is the only contribution to the Lagrangian. If I take the derivative with respect to any coordinate, Lagrangian's partial derivative is 0. So all the coordinates x1, x2, and x3 are all cyclic coordinate. The corresponding conjugate momentum p1, mx1, p2, mx2, p3, mx3, all of them are constant motion. Okay, finally, We consider a simple case, a simple harmonic oscillator. In a simple harmonic oscillator, the kinetic energy is expressed in terms of 1/2 mv squared. You remember, we must not write in this kind of form. This one should be written, should be used for the Hamiltonian. In the Lagrangian, formalism, we must not use P. Instead, we use 1/2 mv squared style. So, we have potential energy 1/2 kx squared. Substitute these two contributions in this form, and the Lagrangian of the system is 1/2 mv squared minus 1/2 kx squared. The conjugate momentum of the system, of this coordinate, we have a single coordinate r. Conjugate momentum x, conjugate momentum corresponding to the coordinate x is obtained by taking the partial derivative of a Lagrangian with respect to the x dot. And if I take a differentiation, what we have is mx dot. So this is velocity. From here, we find that velocity is the momentum, the conjugate momentum divided by mass. Next, we take the partial derivative with respect to that coordinate, x. X dependence appears in the potential energy only, and kinetic energy disappears if I take the partial derivative with respect to x. And the answer is partial derivative with respect to x of minus, this is kinetic energy subtracted by the potential energy, right? Minus 1/2 kx squared. And the partial derivative gives minus 1/2 k 2x. So 2 cancels, so I end up with a minus kx. If I substitute this one and this one into the Euler-Lagrange equation, round L over the round x minus total time derivative of round L over round x dot equals 0. This one is minus kx, and minus, we see mx dot. So time derivative, mx dot, that is mx dot time derivative, that is mx double dot, or time derivative of momentum. Alright, so this one is written in this form, mx double dot plus kx 0. That is the same as what we previously have, x double dot plus k over m, x equals 0, and x double dot plus omega 0 squared x equals 0, where omega 0 is the characteristic frequency, square root k over m. Finally, we want to compute the Hamiltonian. We shall find the Hamiltonian is a function of momentum of position, coordinate, the conjugate momentum and coordinate. Lagrangian must be written in the velocity and coordinate. You must remember. Okay, so x dot multiplied by round L over round x dot subtracted by L. X dot is here, and this is momentum mx dot. This is mx dot squared, and subtracted Lagrangian. 1/2 mx dot squared, and minus, it becomes plus 1/2 kx squared. So this is mx dot squared minus 1/2 mx dot. So the answer is 1/2 mx dot. But I told you Hamiltonian must be written in terms of momentum and coordinate. So x dot x dot should be replaced with p over m. So final answer is Hamiltonian is a p squared over 2m plus 1/2 kx squared. That's it for today.